We now illustrate the use of principal components with a practical example. So we consider these USA arrest data for each of the 50 states of the United States. We have a data set with the number of arrests for 100,000 residents for 3 crimes that are assault, murder, and rape. And we also record urban pop, the percent of the population in each state that lives in urban areas. And therefore, in our data set, we have 50 observations, one for the state, for each state, and the number of features is 4. So we have a matrix X which is n rows and 4 columns, and we can perform PCA after standardizing the variables so as they have 0 variance. And also, this is something I had not said before, when you are using different units, measurement units in your features, you should always standardize. Here, our first choice, as a matter of fact, is to standardize also not only the mean, but also with respect to the standard deviation. So we are working with standardized data. Later we will see what's going to happen if we do not standardize our data. Okay, and this is what we get if we consider just the first 2 principal components, and this is called a biplot. Okay, look at this. You have first principal components and second principal components, and you can have all states plotted in this plane. How is it possible? Well, we are just projecting the 4 features of each state on the first 2 principal components. It's exactly, I will just use this one. It is exactly what happened when I took this value and I projected it onto the first principal component. So I'm projecting this on the first principal component and then on the second principal component. The difference is that in the USA arrest data, the original data are not in a 2-dimension space as this one, but they are in a 4-dimension space. But okay, that makes no difference. I'm just projecting a point in a 4-dimension space on 2 particular directions, the first principal component and the second principal component. So it is interesting that I can project all states, and so I can see that, for instance, for Florida, it almost completely on the first principal component. So its projection on the second principal component is practically equal to 0. And I can also represent in this plane my features. So I can see the relationship between my features and the principal components. So it is interesting to see that assault has a direction which is quite similar with the first principal component. So it seems the principal components is a linear combination of the features where rape, assault, and murder are the most important components. And on the other hand, the second principal components it seems that it has to do mainly with the urban population. Okay, but let's go into some detail. So the blue names are my states. And how do I find the position of the states in the biplot? Just by using their scores. So if I have one of the 50 states, it will have a score for each of the principal components. So I just take the first score, the second score, and I have X and Y that I can use to plot the state in the plot. The orange arrows are the loading vectors of the first 2 principal components. The first 2 loading vectors of the first 2 principal component loading vectors. And for instance, the loading for rape on the first component is 0.54, and the loading or rape for the second principal component is 0.17. And in this way, I can represent all the crimes, that is the features in this case, on the biplot. That this is the name of this figure. It is called biplot because it displays both the principal component scores and the principal component loadings. It is also useful to look at the numbers. So these are the loadings for the first principal component, and you can see, as I said before, that the first principal component has significant loadings for murder, urban assault, and rape. On the other hand, the second principal component, you can see that the urban pop is the largest, as absolute value, has the largest loading coefficient. So the second principal component seems that it has to do mainly with the urban population, while this is a mix of three crimes, we could say. Another interpretation, this is done in a three-dimensional space. We are in a four-dimensional space, but okay, this is closer to our real situation. So we have points that live, we have features that live in a three-dimensional space. Then if we take the first two principal components, we are just identifying a plane in the feature space, and then we are projecting my data. So this could be the geometric representation of the features of the different subjects or the different observations, and I project them onto the plane given by the first two principal components, and eventually I get this plot. This is the result of the projection. We are looking for the crime data, US arrest data. We are just looking at this plot, the result of the projection. And all right, some geometric properties. The first principal component loading vector has this property. It is the line in the p-dimensional space that is closest to the n observations, closest in the sense of Euclidean distance as a measure of closeness. This is interesting because if I want to reduce dimensionality, okay, I have a cloud of points in the feature space. So this is my cloud, and if for some reason I want to reduce dimension, so I don't want to use three-dimensional data, I just want two-dimensional data, I have to find a subspace which is the closest to my data. Okay, if my subspace is just a line, I will have to use the first principal component. But if I are allowed to use a plane rather than just a line, I will look for the plane that is closest to my data, and this plane is the plane identified by the first two principal components. So the first two principal components give me the plane. I can project the data onto this plane, and I can transform my data from three-dimensional data to two-dimensional data. Okay. This is what I'm saying here. So the notion of dimensions that are closest extends beyond just the first principal components. And so in the case of two principal components, you just get the plane that is closest to your original observations. And okay, that's really good. Uh, I've anticipated the issue of scaling. I've said that if you are using different units for your features, then the result of principal component analysis will be sensitive to these units. Therefore, it is highly recommended that you scale your original data in such a way that they have unit standard deviation besides having zero expectation. On the other hand, if you are using the same units, and here in the case of USA arrest data, for instance, rape, assault, and murder, they are all the number of arrests. You might or might not scale the variables. You must be aware that you can get very different results. So if you scale, you have this left figure that we have already seen. If you don't scale, so this is the unscaled vector, things are going to change quite a lot, because you can see that then you have a much larger number of assaults, and so the scale is such that in the end the first principal component has mainly to do with assault, and the second principal component again has to do with urban population. And it is interesting to see that they are more or less orthogonal. Okay. An issue important with PCA is the proportion of variance explained. So far, we have not discussed about the difference of the strength of each component, and the strength has to do with the dispersion along the component I am considering. So let's go back to the usual plot. Okay, so here you can see that along this direction there is a lot of dispersion, not that much along this direction. So here the difference of dispersion is quite substantial, and you could even say that you are going to throw away the second component. You are just projecting your data onto the green axis, and you are just keeping the projected data. So in this case, you will have reduced the dimension of your data from a two-dimension feature space to a one-dimension feature space. But here there is quite a large difference between the variance along this direction and the variance along this other direction. But in general, how can I appreciate the strength? Well, first of all, I have to introduce the notion of total variance present in a data set. Again, we have centered the data to have zero mean, and this is defined as the sum from j equal to 1 to p for all the features of the variance of each feature, and this can be computed as a sample variance. And then we have the variance that is explained by the mth principal component. So I just take the n values of the mth principal components, and I compute the sample variance. Okay, since you just have a rotation when you move from x to zeta, it can be shown that if you take the sum of the variances for the features represented in the original coordinates, or you take the sum of the variances for the transformed features, so they are the features according to they are the principal components. So now, if you take the sum of these variances in this case, or the sum of these variances, in the end, you will find the same result. Here again, we have the issue that if n is less than p, then the number of principal components could be less than p. But for the sake of reasoning, you can consider the case when n is greater than or equal to p, in which case you have a sum from j equal to 1 to p, and here it will be from m equal to 1 to p. So this has to do only with the case when you have less observations than the number of features. Okay, and therefore the proportion of variance explained by a certain principal component will be just its variance divided by the total variance. And I can compute this proportion of variance explained for each of the principal components, and I start from the one that explains the most, and I go on, and I get a plot like this. But usually, or frequently, One refers also to the cumulative proportion of variance explained. So here I have the variance explained by the first principal components, then the proportion explained by the first plus the variance explained by the second, and so on. So in the end, these are the USRS data. I have 4 features, so if I use 4 principal components, I am explaining 100% of the variance. And this plot is useful because if you are looking for dimension reduction, you can decide how many components you are going to use. In this case, you can see that if 1 is not enough because it is about 60%, 2 is something more than 80%. It seems that to have a quite complete explanation of the variance, you perhaps you would need at least 3 principal components out of 4. Okay, but here this was a qualitative assessment that I gave. I could ask, is there an objective way to decide how many principal components I should use? Well, as a matter of fact, there is no simple answer to this question because in this case I cannot resort to something like cross-validation. And one could ask, why not? Well, just think of it. We don't have the target variables, so we do not have something like a response that has to be predicted, and so we can check if we are going to predict it correctly. And as a matter of fact, there could be a case where we have such a response. You might recall of you might remember that we have discussed principal component regression, and in that case we performed the principal component analysis and then regression based on the principal components as new features. And in this case you could decide the number of principal components depending on the success of your regression analysis. So in that case I could use the number of principal components that gives me the best performing regression. But this is quite an exception. In a truly unsupervised setting, there is no objective way of deciding. What can you do? You can look at what they call a scree plot on the previous slide, looking for an elbow. So let's see what I mean by an elbow. Okay. You can see here, you go down. So the hope is that you have a plot where you go down and at a certain point there is a kind of angle, there is an elbow. So if you add principal components, their contribution becomes small, and or also in this cumulative plot, you hope that you have a plot where you go up with a few principal components, and then after a certain point you are already quite close to 100%, so you are about 95-96%, and all the subsequent components are adding just a tiny contribution. So this is a possibility about principal component. Okay, the choice of the number of components and that I should use to summarize my data. We are ready for the next topic, that is clustering. And the clustering refers to set of techniques for finding subgroups in a data set. So the idea that I have my data and I would like to partition them in groups that have this characteristic, that all the data in the same group are quite similar. Of course, I should specify what similar is going to mean, or what different is going to mean. And in many cases, this will depend on the domain. So this will depend on the type of data you are working with. But we can give some general considerations. And what's the difference between PCA and clustering? On one hand, PCA looks for a low-dimensional representation of the observations with the aim of explaining a good fraction of the variance. On the other hand, clustering looks for homogeneous subgroups among the observations. So they are two facets of unsupervised learning. Uh, why should I be concerned with clustering? There are a number of interesting applications. For instance, I could have lots of data for a large number of people, and I could want to perform what's called profiling, that is, make a segmentation of my customers, for instance, that identify subgroups that are similar. So my hope is that if I clusterize my customers, then I could find groups that are more receptive to some form of advertising, or that are more likely to purchase some types of products. And this market segmentation task is just equivalent to clustering data in unsupervised learning. We will consider first k-means clustering, where we try to partition the observation into a pre-specified number of clusters. Let's illustrate this by an example. So we have a simulated data set with 150 observations in a two-dimensional space. These three panels show the results of k-means clustering when I decide different numbers of clusters. So here I decide that I want 2 clusters, here I want 3, and here I want 4 clusters. There is no ordering on the clusters, so the colors are arbitrary. So for instance, here you have blue, and here the blue is down, and here it is on top again. And however, the colors are useful because you can see immediately the results of clustering. So here you have 2 clusters. This was the result. It seems reasonable. You could question whether some points on the here on the border should belong to the first or the second clusters, but overall you're quite happy. Here it becomes more questionable if you really need 3 clusters, because here these 2 clusters are very close to each other, and this could seem like an homogeneous cluster, but there's no objective way to decide. And here it is even more questionable that you can do with you really need 4 clusters. So you see, you have to decide in advance the number of clusters, and then you get your results. And it could be that you are using too many, or that the clusters are insufficient to represent your data in other cases. Details. We denote by C1, C capital K, the sets containing the indices of the observations in each cluster, and we are looking for what's called a partition. So the union of these sets should be the the whole set of my observations, and these sets should be disjoint. So, in other words, if I take an observation, it should belong to one and only one cluster, and the union of all the clusters should therefore include all my observations. notation. If the ith observation belongs to the kth cluster, we will say that I belongs to ck. The idea behind the k-means clustering is that a good clustering is one for which the within cluster variation is as small as possible. What do I mean by within cluster variation? This is a measure that we call WCV, of course, a measure applied to the kth cluster. This is a measure of the amount of by which the observations differ from each other. So it tells you how compact is the cluster, and therefore our final problem will be find the clusters C1, CK that minimize the sum of the within cluster variations computed for all clusters, and then these measures are added up to find the final cost function. Okay, so the within cluster variation summed over all k clusters should be as small as possible. How do we measure within cluster variation? Usually we adopt a Euclidean distance, so we are taking all the possible squared differences between the features of the different observations. So I have observation I and observation I prime. I take all the features. So it's like I have two vectors and I compute the norm or the square norm of the difference between the two vectors, the vector xi and the vectors xi prime. And I have to do this for all the vectors, for all the observations that belong to the kth cluster. And I compute this, and then I compute an average distance by dividing by the cardinality of the cluster. So this is the number of items that belong to the kth cluster. In the end, I have to repeat this for all the clusters. So I have a sum from k equal to 1 to capital K that is the number of clusters, and this is my cost function. And the k-means is a nice algorithm, very simple, very very short. You can explain it in just one slide. So you start with a random assignment of the observations to the clusters. So I take each observation and I just randomly extract a number from 1 to k, so completely random at the beginning, and then I have this iteration. For each of the clusters, I just compute the centroid, that is the mean, the vector which is made by the means for each feature computed using the items belonging to that cluster. And in this way, I'm going to update the centroids of my cluster. Once I have new centroids, then I repeat assignments. So I take each observation, and I reassign it to the centroid which is closest, where closest is defined according to the Euclidean distance. And then I start again. At this point, the observation will have moved from one cluster to another, and therefore I can compute again the centroids, because if a cluster has changed its items, it will have a different centroid. I update the centroids. Having updated the centroids, I'm looking whether some of the items are going to be moved from one cluster to another one. And okay, and I go on until the algorithm stops, because at some point I will not be able to move any item from one cluster to the other because they already belong to the closest centroid, and therefore I will not be able to update the centroids as well. And this algorithm is guaranteed to decrease the value of the objective function at each step. Why? This is a good question. There is just some algebra. If you look at this cost function, at this within cluster variability, you can see that you can write this in this way, where x bar is just the mean for feature x bar kj is the mean for feature j, and hence it happens that at each of the two steps of k-means, you are always decreasing this quantity, because if you keep the centroid fixed, then you are you are moving the observation in such a way that you are decreasing these distances, because you are moving one observation from a cluster to another cluster where the difference is smaller. And when you update the centroids, you are keeping fixed your observations, and you are just updating the x bar in such a way that this becomes smaller. So both steps are decreasing the cost function, so you can always you are going to increase always decrease the value of the objective, but you are not guaranteed to find a global minimum because this is a kind of greedy algorithm. So it could be that in the end you stop with a certain configuration, but if you could move two or more items from one cluster to the other, it may be that you are going to improve your final cost. And let's see first how this is going to work in practice. So these are the data. This is the first step, which is random assignment. And if you have a random assignment, usually you will turn out to have the centroids quite close, because the data were assigned randomly, and therefore each cluster has data that are almost everywhere, and on the average the centroids will be close to each other. Now I reassign the items, and even if the centroids are close to each other, you can see that I get quite meaningful clusters. Once I have assigned my observations, I update the centroids, and since the clusters are quite sensible, now I have centroids that are different from each other. And you can go on until convergence, and you see that this finally is not very different from the second iteration. So it's an ingenious algorithm that works quite well. And here, okay, this is the explanation, but I think that I can skip now. And this is the effect of different starting values. This is about the fact that you cannot guarantee that you're going to find a global minimum. So the algorithm was initialized several times, 6 times, and these are the results. And you can see that here is the cost function, and the cost function was minimized in these 4 cases. And in these 4 cases, you see that actually you just have the same result. But there are 2 cases, this one and this one, where the algorithm stopped with a different configuration, and you can see that the cost function is greater, and also the clustering, even visual inspection confirms that it is not as sensible as this one, maybe because you can see that you have this strange cluster here, which is not very compact, and as a matter of fact, the cost function tells you that you did worse than in this case. But this shows you that the initial starting value could lead different initial starting values could lead to different final results. So you are advised to run the algorithm several times, starting from different initial values. And here is the explanation of the figure. So I think we can skip, and at this point we are done. Okay.